For this problem, we have a 30 kilogram disc. We're assuming it's a uniform disc, and it is pinned at point O, and it is subjected to an external force 50 Newton, and as a result it rotates counterclockwise with an angular velocity of 10 radian per second, and we need to determine tangential and normal components of reaction of the pin support point O, as well as the angular acceleration of the disc. So if we draw the free body diagram, the force 50 Newton can be resolved into a horizontal component of 40 Newton and a vertical component of 30 Newton. And then here we have the support reactions from point O. The direction will be along the normal and tangential direction. So the tangential direction, so actually let's draw the kinetic diagram first. If this is point G, the gravitational center, we will have M, a G, T in this direction, and then the normal direction will be pointing towards the center of rotation, so M, A, G, N. And then we have a counterclockwise rotation, therefore IG alpha in this direction. So as you can tell, we should draw our unknown forces ON in this direction and then OT in this direction. And lastly, we would have weight. So unless the problem says that the motion is in horizontal plane, or if we are told that we can neglect the weight, otherwise we should include the weight. So weight is 30 kilogram times 9.81. So at this point, we have completed the free body diagram and the kinetic diagram, and we're ready to write our three equations of motion. So our resultant force along the normal direction, we will have ON minus the weight 30 times 9.81, and also plus the 30 Newton component force. And on the right hand side, that equals to MAGN. And because this is a problem involving rotation about a fixed axis, the axis is the one that is perpendicular to this screen and passes through point O. Therefore, because of that, we can rewrite this equation into M omega square R. So that equals to 30 times the angular velocity 10 squared times R is this right here from point G to the rotation center, and that is the radius of this disk, 0.3 meter. So as you can tell, in this equation, we only have one unknown, which is ON. So ON can already be evaluated here, and that is 1,164 Newton, or 1.16 kilonewton. And then resultant force along the tangential direction, that is to the right, we will have OT plus 40 Newton force, and that equals to MAGT, also can be rewritten as M alpha R, and that is 30 times R is 0.3, alpha is another unknown. Therefore, we need to write a third equation, which is the moment equation. Because we have two unknowns at point O, we're going to summarize the moment about point O so that the two unknowns O and OT do not show up in our equation. So the weight force also have line of action passing through point O, therefore the weight does not have moment about point O. So we have the 30 Newton force with counterclockwise rotation, and the moment arm is 0.3. And we also have the 40 Newton force. It's also creating counterclockwise rotation with a moment arm also 0.3. And on the right hand side, this equals to IO alpha, which is IG plus MR squared alpha using the parallel axis theorem. IG is the mass moment of inertia of this disk about the axis passing through point G perpendicular to the plane, and we have a formula for that, and that is 1/2 mr squared plus another mr squared alpha, and that equals to 1/2 times 30 times 0.3 squared plus 30 times 0.3 squared alpha. So from the third equation, we can solve for alpha, and alpha is determined to be 5.19 radian per second squared. And then we substitute that value into the second equation. We can solve for OT to be 6.67 Newton. So now we have solved for the angular acceleration of the disk alpha, as well as the two force components of the support, pin support at point O. So that solves this problem.